Okay, let me start. So I will just review what we did last time before I start anything new today. Okay, so last time we introduced the concept of a matrix, which is nothing but an array of numbers that has a number of rows and a number of columns. And these numbers of rows and columns, they determine the size of the matrix. So, for example, when we say that we have a matrix of 2 by 3, this means that the matrix has 2 rows and 3 columns. So the total number of entries in such a matrix is going to be 2 times 3, which is 6 entries. So there are 6 numbers in this matrix which determine the matrix itself. Okay. We also said that we're going to refer to an entry in the matrix by the number of row and the number of column at the intersection of which this number lies. So, for example, if I want to refer to number 1 here in this matrix, then we see that it is in row 3 and in column 3. So I would say it's entry 3, 3. Okay. And you can do the same for any other entry. For example, if you want to refer to this entry here, which is number 5, then it is in the second row and it is in the first column, so it is entry 2, 1. Okay, so the first number 2 is referring to the number of row, and the second number 1 is referring to the number of column. These numbers 2 and 1 are usually called the indices or subscripts of the entry. Okay, and usually we write them. So let me just pick my. Oh, do you know what? Let me just open a new jam, because we'll be using the jam anyway. Here's a new jam. Okay, so title it matrices. Okay, so for example, as I said, if I want to refer to this entry, which is number 5 in the second row and the first column, then if I call this matrix A, let's say, okay, then I would refer to it by writing A to 1. Okay, A to 1. So it's not 21, it's 2, 1, where 2 here is referring to the number of row and 1 is referring to the number of columns. So this would be equal to 5 in that matrix, in our matrix. Okay. Good. Okay. We also introduced the zero matrix, which is a matrix made completely of zeros. So all the entries are zeros. It could be of any size. The size is not important. Any matrix which has all its entries 0, then we call it the zero matrix. So there are many zero matrices, not a single one. Yeah? But any matrix whose entries are zeros, we call it the zero matrix. Okay. Now we also said that when it comes to comparing matrices, the size matters. So it doesn't make any sense to compare two matrices of different sizes. For example, it doesn't make sense to compare a matrix of size 2 by 3 to a matrix of size 3 by 2. These are completely different matrices. So let me just recall to your mind. So if I have a matrix, let's call it A, let's say, okay, and the matrix A is, suppose it has the following shape. So 1, 0, let's say 2, -1, 3, and 7, okay. It doesn't make any sense to compare it to a matrix of this form. Say, for example, 1, 2, 3, 1, and compare two matrices only if they have the same size. Okay, and remember, in that case, we say that matrix A is equal have same size, and so this is the first condition, and the second condition is this Aij, which is the entry number ij. Oops. I hope you understand this distinction. This is for every, right? For every I and j, right? For every I and j. So no matter what I and j you pick, of course, within the range, Aij has to be equal to Bij. Only then can we say that the matrices are identical or equal. Okay. And also, we introduced last time. We introduced. Okay, I left it, so it's somewhere here. Yeah. We introduced now the first operation, which was the addition of matrices, right? We said that if two matrices have the same size, they should be the same size, otherwise we can't add them. Then the sum of these two matrices is just the sum of the corresponding entries, or as we say sometimes, it's the sum which is taken entry-wise. So entry by entry. So you take, for example, this entry in this matrix and you add it to the corresponding entry in the second matrix, and you then move on to the next entry and so on, and you do it for every entry. So you are adding entry by entry, but for this to work, they should have the same entries, right? And this means that they should be the same size. So you can't add matrices unless they are the same size. And if they are the same size, then the addition is done entry by entry, or entry-wise, as we say. So for example, here, if I want to find the sum of these two matrices, let's say, then what I'm going to do now is take the entry 1, 1 in matrix A and add it to the entry 1, 1 in matrix B. And this will give me 6, you see. And then you do the entry 1, 2 in matrix A, you add it to the entry 1, 2 in matrix B, and you would get 4, right? And so on. And you keep doing it, okay? And of course, you will get a matrix which is the same size as A and B. So the size of the addition, or of the sum, of the two matrices is going to be the same size as A and B. Okay? And again, just to remind you, A and B should be the same size. Otherwise, you won't be able to add the matrices. Okay. So what properties do we know of this addition? The addition is commutative, which means if you switch the order of the two matrices, the result, the sum of the matrices does not change. And this is quite obvious because basically you are adding numbers, right? You are adding numbers, and you know that if you switch the order, for example, if you add 1 to 5 or you add 5 to 1, stays the same, does not change, right? So that's why if you switch the order in the matrix addition, the result of the addition does not change. Okay? Similarly, for the same reason, we know that the addition of matrices is also associative, okay? Which means that you can group them. You can group them in this fashion, or you can group them in this fashion, and the result of the addition does not change. And this is a consequence of the fact that addition of real numbers is associative. Because of this, the addition of matrices also is going to be associative. Now, there is also an identity element for the addition of matrices. It is the zero matrix. So if you take the zero matrix and you to a matrix of the same size, of course, it has to be the same size, then you will get the same matrix. So for example, here, let's say, if here we had instead of this matrix, let's say we had the 0 matrix, which means 0, 0, 0, all the entries are 0, then you can see easily that if you add all the zeros to the corresponding numbers here, right, then these numbers will not change, will stay the same. So for example, 1 plus 0 would be 1, 2 plus 0 would be 2, 3 plus 0 would be 3, and so on. So adding the 0 matrix to a matrix of the same size does not change the matrix. And this is what we mean by saying that the 0 matrix is an identity, which means you add it to any matrix, it does not change it. Okay? I will come back to this a little bit later when we introduce multiplication by a number, or what we call usually scalar multiplication. But essentially, these are the basic properties. And that's all what we have done last time. Do you have any questions?
No, doctor.
Okay, today I want now to introduce scalar multiplication of matrices, which means multiplying a number by. So how do we multiply a number by a matrix? The operation is very simple. You multiply every here, you see, and you want to multiply it by the number 3. So what does it mean, multiply the number 3 by a matrix? It means you take every entry and you multiply it by 3. So for example, this entry will become 3, this entry will become 6, this entry will become 9, this will become 12. You just multiply the entry by the number 3 in this case, okay? Every entry. And that's it. So again, it's a multiplication of all the entries by the scalar. This number is usually called the scalar because it's the scalar. So we just multiply every entry in the matrix by the corresponding scalar. Okay? And that's how we define it. So if we have this matrix A, which is given by its entries Aij, and we want to multiply it by the number k, right? Then the result is going to be, you see, a new matrix, right, which is the same size as A, but now every entry of this matrix will get multiplied by the number k. Okay, so let me just do an example. Let's say we want to multiply this matrix A by 2. Let's say I want to multiply A by 2. Okay, then what do I get? Let's see. If I want to multiply the matrix A by 2, then this entry here would become 2. This would be 0. Here I will get a 4, then minus 2. Then this one will become a 6, and this will be a 14. And you see now, this matrix had the size 3 by 2, right? And the resulting matrix here, after multiplication by a scalar, also has the same size, 3 by 2. So you see that the size does not change. Okay. In the same fashion, I can multiply the matrix B by any number. So let me try to multiply it by -1. So what does it mean to multiply B by the number -1? Okay. This means that, so now every entry of matrix should be multiplied by -1. So the first entry here would be -1, then -2, then -3. This one would not change, of course. This would become 1, and this would become -7. Okay. And you see that every entry now in this matrix, in the new matrix, is a negative of the corresponding entry in the matrix B. So now let me try to add these two matrices. So what do I get if I add the matrix B to the matrix B multiplied by -1? Okay. So what do I get if I add them? Okay. Let's see.
0.
Yeah. So I get 1 plus -1. So the first entry here in the first row is going to be 0. Then 2 plus -2, which is 0, right? Then 3 plus -3, which is 0, right? Then 0 plus 0, of course, is 0. Then -1 and 1 is 0, and 7 and -7 is 0, 2, right? So I get a matrix which is 0, and usually it's 0, right? So you see B plus -1 times B is the 0 matrix, okay? And because of this, this matrix is said to be the inverse of the matrix B. And usually it's written in this way. It's written simply -B, okay? But -B is just -1 times B. But we write it -B because when we add it to B, we will get the 0 matrix. Okay, so this is called the inverse matrix. Okay, it's called the inverse matrix to the matrix B, and you can define it for any matrix, not only for B. You just have to change the entry into its negative in the matrix. So, for example, if I want to get the negative inverse of A, I simply change every entry in A into its negative. Right? So I get -1, 0, -2, 1, -3, and -7. Okay. And
Doctor,
of course,
why
you
is
can
A to 1?
Say it again.
Why is A to 1 5?
I could not hear you. Please say it again, please. Repeat your question.
Why did you wrote A to 1 is equal to 5? Why?
This is from the book, from here. It was, oh, I skipped it already. Yeah, A to 1, it was for this matrix. So you came late, I see, right? This was A to 1. A to 1 equal to 5. This entry was 5. Okay? Forget about this one now. Let me call it, do you know what? Let me call it not A. Let me call it B. C. We have already B. Let me call it C. So this is C. This matrix is called C. Okay. So now we defined also the inverse matrix. This is what they wrote here. And the inverse matrix is just the matrix with all the entries changed to the negative. Right? So you just multiply every entry by -1. Okay. So now what properties do we know for the multiplication by a scalar? First of all, it is distributive over addition. So this means if you are adding two matrices, let's say A and B, and then you multiply the result by K, it's the same as multiplying each of the matrices by K and then adding the two results. Remember, this property is called distributivity, right? It's like in multiplication of numbers. You can, if you are adding numbers and then multiplying, you can multiply first and then add, right? So this is what we call distributive property. Also, we can add the scalars and then multiply by a matrix. It's the same as multiplying each of the scalars by the corresponding matrix and then adding the result. Okay. Associativity here for multiplication by a scalar, and of course multiplying by 1 is an identity. So 1 times A, if you multiply the matrix A by the number 1, then nothing will change. All the entries will stay the same because you are multiplying each of them by the number 1. So we will get back to matrix A. Right? And this is true for A. Okay? Maybe I should give you an example. So let me try to give you an example on this here. So what do I mean by this property, and maybe this one too? Okay, although these are, I mean, quite easy, but just to be sure that you get it. Okay, so let's say we have two matrices, A and B, and let's keep them simple. So I will take my matrix here to be 2 by 2. Let's say -1, 2, 3, and 1. Let's say, and the matrix B also 2 by 2 in order to be able to add it to A. And let's say we have 0, 1, 1, and -1. Okay. And suppose, according to this, I want to multiply now the sum of A and B by a number. Let's say I want to find 3 into A plus B. Okay. So what I can do is first find A and B, find A plus B, and then multiply the result by 3. Okay, so let's try to find A plus B. So what is A plus B? We get
-1, 3, 4, 0.
3. Yeah, 4 and 0, right? And now you multiply by 3, according to the definition. So you multiply every entry by 3. You get -3, 9, 12, and 0, right? Or if you want, you can do it this way. You can multiply 3 by A and add it to 3 multiplied by B. Okay, so let's see whether we get the same result. Okay, so let's see, what is 3 times A? We want to multiply A by 3. So what do we get? We get -3, 6, 9, and 3. Okay, plus now 3 multiplied by b would be 0, 3, 3, and minus 3. Right? And now if you add them, and we know how to add such matrices because they have the same size. Yeah, we get 0, 0 from here plus minus 3, so we get minus 3, right? And here we have 6 and 3, which is 9, right? And then we have 9 and 3, which is 12, and 3 and minus 3, which is 0. And you can see that the result here and the result here are identical. And this is what the property is telling you. So you can, if you like, do the addition first and then multiply by the scalar, or multiply by the scalar first and then do the addition. The result will stay the same. Okay, and this property is called distributivity of scalar multiplication over addition of matrices. Okay, and in the same fashion, I'm not going to do it. You can simply add first the scalars and then multiply it by a matrix, or if you want, multiply each scalar by a matrix and then add the result. I will leave it to you to check this. This is so simple. You can check it easily. Okay. Any questions? Any questions about this?
No, doctor.
Okay. Good. Now we come to something which is completely new. Now we want to define multiplication of matrices. Okay, so now I would give you now 2 matrices, and I would define now a new operation on these 2 matrices, which I call the multiplication of matrices, that will result in a new matrix. It will give me a new matrix, okay, and this new matrix, of course, will depend on the original matrices, okay. But before, I already introduced this kind of terminology. If you remember, if you have a matrix which is only a single column, right? Only a single column, we call it a column matrix or a vector. Okay, so this is a vector. Okay, and if we have a matrix which has only a single row, okay, we call it a row matrix or a row vector, if you want. Okay. So these are going to be, frequently met in this course. So we'll meet them frequently in this course, and it's good to remember that whenever I refer to a vector, I mean a column, right? And if I refer to a row vector, I mean simply a single row. Okay. Okay. So now we can. Okay, so this is not quite what I want here, but anyway, let's now try to look at our system of equations. So remember that we started with the system of equations, right? So let's start with the system of equations and try to write it using these vectors. Okay, so you can see here that so if we have a system of m equations. So the first equation, the second equation, and then m equation in n unknowns. So there are n unknowns, x1, x2, xn, okay? Then it turns out you can write this system as a sum, right, of what? Of a vector, you see, multiplied by a scalar. Now, we know what this means, because this is a matrix. Remember, this is a matrix. And we know what we mean by multiplying a number by a matrix. It means you multiply every entry, right, of this matrix by this number, okay? And then we also know what it means to add this matrix to this matrix, right? We know, we just add the corresponding entries, okay? So now this system can be written in this fashion, okay? And what is this? What is this? This is a vector here multiplied by the unknown x1, then a second vector multiplied by the unknown x2, and so on. Okay, so before I move on, let me give you an example of this. Okay, just to make sure that you understand this kind of notation. Okay, so let me put here, let's say, some lines, and let's try maybe to write this system 2x, a simple one first, 2x plus 3y. Is equal to, let's say, 5, okay, and then minus x plus, let's say, 2y is equal to -2, let's say, okay. So I want to write this system using this notation, using the vectors, which are the column vectors. Okay, so how are we going to do it? Look, I can write it this way. I can write x, this is my variable, into the first vector, which is 2 minus 1. You see? Here, these two and minus 1 here, plus y into 3, 2, right? Equals, okay, to the number 5 minus 2, okay? And now, as a matrix, you see, if I want to write as a matrix, this is telling me, now I know what this means. If I multiply x by 2, by this vector, it means here I have 2x, and here I have minus x, right? This is what this means. Plus, in the same way, if I multiply y by 3, I have 3 times y, and here I have 2 times y, right? And this should be equal to 5 minus 2. Right? And now I know what the sum of these matrices. It means I need to add the entries, entry by entry. So the first entry I will get 2x plus 3y, and in the second entry I will get minus x plus 2y. Right? And this should be equal to the vector on the right, which is 5 and minus 2. Okay, and now we have equality of matrices. So when are these matrices equal? They are equal when their entries are equal, right? So this means from here I can conclude that 2x plus 3y is equal to 5, and of course also minus x plus 2y is equal to minus 2. Okay, and this is my system. Okay, so you see that this system can be written in this matrix form. I can write it in this matrix form. This might be useful. Okay, we're going to see also another way of writing this system, but this is one way. This is one way in which we can write a system of equations. We can write it as a sum of vectors. So each of these is a vector. You see, each of these is a vector, and we are multiplying each vector by the unknown, x and y, okay? And this is usually called a linear combination. This is called a linear combination of these vectors, okay? So here we have, it's a combination, right? Because we are combining them into a single sum, and it's linear because we are using just the vectors multiplied by some unknowns, x1, x2, and xn, okay? So a system of equations, just to say it once more, a system of linear equations is equivalent to a linear combinations of n vectors. Okay, and each vector has m entries. You see, this is a11, a21, and am1, and so on. For each vector, there are m entries in it. You see. Any questions about this linear combination stuff? Any questions? Okay. Now, it turns out that there is a nice way, right, of writing this linear combination, okay? And this uses what we call the matrix multiplication, okay? The matrix multiplication of two matrices, okay? And now I will show you now, so here, let me see what the book is doing here. Okay, so the book is introducing first the multiplication of a vector by a matrix. Okay, but effectively we can do it this way. Okay, so let me just try to first introduce the multiplication of a vector by a matrix. So here we have a vector, right? You see, and here we have this matrix. Okay. And I want now to define a new operation, which is the multiplication of this matrix by this vector. Okay. Now here I have to warn you at the very outset that the order matters. The order. So here we are multiplying the matrix from the left. You see, we are multiplying it by the vector from the right. So the multiplication of the two objects here has a specific order. Okay, so the matrix is coming from the left, the vector is coming from the right. Okay, how do we define the operation of multiplication between a matrix like this and a vector like this? Okay, so first of all, okay, and it's going to be crucial. The number of columns in the matrix, okay, has to be the same as the number of rows in the vector. So here there are 3 columns, you see, and here there are 3 rows. Okay, so this number, 3 columns and 3 rows, 3 and 3, they should be equal. Otherwise, the operation is undefined. We can't define the operation. Okay, and then what do we do? Now, what do we do now to multiply this? Look what I do. Okay, so I'm going to do it somewhere here. I'm going to do it somewhere here. So let me take this example. I would like if you can read to me, please, these numbers, okay? So I can copy them. I'm not sure whether you have access to this. Let me title it.
1, 2, 3.
Say it again, please.
1,
2, 3.
Yeah. Yes.
4, 5, 6.
Okay. These are simple, right? 4, 5, 6. Okay.
7,
Yeah.
8, 9.
Okay. Yeah. 7, 8, 9, right? Yeah. Okay.
Yeah.
So these were easy. 7, 8, 9. Okay. Good. So now, how do I multiply this matrix by this vector? Okay. So notice that the size of this matrix is 2 by 3. You see, the size of this vector, of course, is 3 by 1. Okay. And see, this 3 and this 3, they are the same, right? Only in this case can I multiply, okay? If these numbers were different, let's say we have here 2 by 3, and then here we had, let's say, 4 by 1, then the operation would be undefined, okay? Now, what is the result? The result is going to be a matrix which is 2 by 1. 2 by 1, you see this, 2 by 1, okay? So I need here, so what does mean 2 by 1? It means it has 2 rows, right, and 1 column, okay? So I need to prepare now a matrix with 2 rows, okay, and only 1 column. So perhaps maybe I'll make it a little bit wider so it fits here, and I will show you why. Okay, now, so how many entries will there be? There will be 2 entries, right? Because I have 2 rows and 1 column. Now, how do I get these entries? How do I get these entries? Look what I do. And you have to be careful here. I take the first row here, you see, okay, and I will call this operation pairing, and I will describe it to you. And I pair it now with this column. So what does it mean to pair it? It means you take the 1, you multiply it by the 7. This one, you multiply it by the 7. Then you take the 2, you multiply it by the 8. Then the 3, you multiply it by the 9. And you add all these numbers, okay? So 1 times 7 is 7. 2 times 8 is 16. And 3 times 9 is 27.
27.
Okay? So the first entry here is going to be 1 times 7 plus 2 times 8 plus 3 times 9. Okay? Now the second entry, you do exactly the same now, but with the second row, with this one here. The second row. So now you take the second row and you pair it with the column. Okay, so you do 4 times 7 plus 5 times 8 plus 6 times 9. Okay, so let's see. 4 times 7 is 28. Plus 5 times 8, which is 40. And finally, 6 times 9 is 54, right, as we remember. Okay, and let's see, what do we get then? We get 27 and 7, 34, and 16, 50, right? This is 50. Okay, and then we have 28 and 54. This is 82. So it's 122, I think, right?
Yes.
Okay, that's it. So this is our new matrix, and you see that our new matrix has 2 rows. This is a number here 2. This is why we got here 2, and it has 1 column. You see, and this is because we had here 1. Okay, and now we have defined the multiplication of this matrix, right, by this vector. Okay, let me show you one more example. This is going to be crucial because later on we shall use it to define matrix multiplication in general. Okay, so let's now take another example. See how we multiply a matrix and a vector. Okay, I'll make it a little bit, maybe a little bit more complicated. So let's take this. Let's say 3 by 3 now. Oops, 3 by 3 matrix. Let's say we have 1. I'll put a little bit of zeros here to make it easier. 0, 2, 1, 0, and one more. Let's say 3, negative 1, 1. Okay. I want to multiply it by this vector, which has, let's say here 2, 1, 1. Okay. Now, so before I begin, I want to know what result to expect. What should I expect? Okay, so this matrix has 3 by 3, and this vector has 3 by 1, right? And first of all, I noticed that this 3 is the same as this 3, so I can now do the multiplication. You see, because the number of entries here in a row, the number of entries here has to be the same as the number of entries in a column, right? Otherwise, you won't be able to pair them. You won't be able to pair. If you had here 3 and 2, then one entry would be missing in the column, right? So you should have the same number of entries in a row in the matrix as the number of entries in a column in the vector, okay? And so what should I expect? I should expect a vector which is 3 by 1, right? 3 by 1. Okay, so I need to prepare here a vector which is 3 by 1. Now, okay, so let's see. Now this should be easy because the numbers are small here. So what do? 1 times 2 plus 0 times 1 plus minus 1 times 1.
Minus 1, you get 1.
Yeah, so it's 1 times 2, which is 2. 0 times 1 is 0, so we simply ignore it. And minus 1 times 1 is minus 1, so it's 2 minus 1, so it should be 1. So the first entry here is 1. Now the second entry. Now to get the second entry here, I need to use a second row. I will do the third entry first. So if I want to find the third entry, I need to use the third row, this one here. Okay, so let's do it. How can I do it? I have to pair it with the column. Okay, so I take 3 times 2. 6 plus minus 1 times 1, which is minus 1, and plus 1 times 1, which is 1. So I get 6 minus 1 plus 1, which will give me 6. Just 6, right? And finally, to get now the second, row, the second row with a column. Okay, and the pairing is exactly the same. So I do 2 times 2 plus 1 times 1 plus 0 times 1. And if you do it, of course, you will get the 5, right? So you get a vector, which is 3 by 1, and this vector has entries 1, 5, 6.
دكتور بس ما انتبهت ليه أخذت عملت آخر entry بعدين السكند entry.
لا, it doesn't really matter which order you do it. You can do it in any order you want.
ماشي.
Okay. Any questions about this multiplication?
Yes, doctor.
Yes. Yes, Samar.
أنا ما فهمت ليه طلعوا 5 و 6.
Yeah, okay. So let me just, do you understand the 1? Do you understand this one here?
Yes.
Okay. So let me try to re-explain the 5. So how did we get this 5? Okay. So look what you do. You take this 2 and you multiply it by this 2. Okay. So what do you get? If you multiply 2 by 2, you get a 4, right? And then
okay. نحن عملنا multiplication بأول.
You multiply it by this one, okay? And you add it, so you get a 1. And finally, you take this 0 and you multiply it by this one, right? But you get a 0. So if you add all these, you will get a 5. And this is this 5 here.
Okay. خلص أنا فهمت 6. أنا بس ما كنت فاهمين الفكرة.
Yeah, and the 6 in the same way, but use now these numbers instead. Use now these numbers here. Okay.
Yes, doctor, thank you.
Good. Okay, now let's see. Can we multiply, if we want to follow the same procedure, can we multiply, let's say, a matrix which is, suppose, let's say 2 by 3, can we multiply it by a vector which is 2 by 1? So just to illustrate, so let's say I have a matrix which is 2 by 3, 1, 0, 1, 0. Let's say we want to multiply a vector which is, let's say, 1, 2. Can we define this? Is it defined? 2 by 3.
No.
This is 2 by 3, and this is 2 by 1. Okay. Can we define the multiplication?
No,
If you try
No.
yeah. So I'm not sure what I heard. I think you said no, right?
Yes, since
Yes.
the number of row doesn't equal to the number of column.
Yeah. Yes, absolutely right. Yeah. If you try to do the multiplication, just say we did it here. So for example, you take the first here and you begin it with the column here. You see, you will be able to pair this one with this one, right? And then this one will be paired with this two, but you will be left with this one here, right? This one will not be paired to anything in this column here, right? Because this column contains only 2 entries, while the row here contains 3 entries, right? So it's not possible to define the multiplication. And that's why we require that this number, which is the number of rows, the vector, must be equal to the number of columns in the matrix. Otherwise, the multiplication is undefined. We can't define the multiplication. Okay? So this is essential. If this is not true, then you can't find it. You can simply do the multiplication. Just follow this procedure. Okay. I think I would stop here for today. I may assign a little homework for the next time for you to practice, maybe not multiplication, because I'm not done with multiplication yet. We will come back to multiplication. At least to practice the addition of matrices, multiplication by numbers, identities, and so on. Do you have any questions?
No, Dr. Santa.
No, everything is clear.
Yeah. By the way, I sent you the correction, right? Not the correction. I mean the corrected graded homework. So I hope you all received it. And if you have any questions, you can ask about the correction, about the grading, about your mark.
Doctor, I have a question actually.
Do you have a question?
Yes.
Yes, please. Yes.
Will our partial grade will be taken from the homeworks, or will we do a quiz or something?
Of course, I'm not sure about it, but of course, in my plans, I have a quiz. So at some point, we will have a quiz. But these graded homeworks certainly will count. As I mentioned in the homework itself, I said that it counts 10% towards your final average. So yes, it certainly counts.
Okay, thank you.
Okay, that's it for today. Then see you next Tuesday. And as I said, there will be a homework.